Welcome everyone to this recording, continuing our discussion on cluster analysis. Before we get going here, I'd just like to remind you that project number 2 is due on class time, or at class time on November 6th. Okay, so last time we were talking about a particular example. We were talking about the nearest neighbor method. This is an agglomerative clustering procedure, and we were discussing this very simple example involving 4 observations. I want to make one quick clarification here, and you can see my handwriting there in blue representing it. So we have two variables in this data set. Let's just call them variable 1 and variable 2. And each observation is denoted by, let's say, x sub I for I equal 1 to 4. So in this particular case, x1 represents 2 and 3.4 transpose. x2 is 4 and 5 transpose. x3 is 6 and 3 transpose, and x4 is found in a similar manner. Just wanted to clarify that because this x1 and x2 here might be a little bit confusing. That was meant to represent variable 1 and variable 2, essentially. Okay, now with that, let's just review a little bit how the nearest neighbor method works. Oops, hold on a second. So we have this plot that we were looking at on page 11, and we have the 4 observations plotted. We have the Euclidean distances between the observations also given there as the midpoint between 2 observations. And the way that nearest neighbor clustering starts is to first of all represent each observation as a particular cluster. And then we need to decide, well, which 2 clusters do we want to join? And this is determined by taking a look at, well, which clusters are most similar or nearest to each other. And we see here that observations 3 and 4 are the nearest, so that forms a particular cluster. Now, all agglomerative clustering methods start this way. They try to find the closest 2 observations to each other to form the first, let's say, cluster that has more than 1 observation in it. Now the second step then is what's different amongst these various agglomerative clustering methods. We again in the second step want to join together clusters that are the closest together, or the 2 clusters that are closest together. And to do that, then we look at these distances. So obviously, for example, the distance between 1 and 2 is 2.56. The way that the distance between observation 1 and the cluster that has 3 and 4 is defined by the nearest neighbor method is that we look at the nearest neighbor to observation 1. In that case, it's 4. So the distance between cluster that has observation 1 in it and the cluster that has observations 3 and 4 in it is 2.44. Since 2.44 is less than 2.56, we join them together. And then in the very last step then, we would then of course join all the observations together into a single cluster. Now let's talk about how I actually drew this plot here in R, because I think it's kind of a cool plot that helps really demonstrate what this particular clustering method does and what other clustering methods will do later in today's lecture. So the actual code is located starting on page 10. So let me go to my corresponding program. I'm going to make this a little bit bigger too. In the dist underscore example program, what I have here, for example, is I put all my data into a data frame called set1. Let me also make this a little bit bigger too. And in order to find all pairwise distances between pairs of observations, I use the dist function. And then and we saw this last time. And in order to make this function a matrix format, I use the as.matrix function. And so we see, for example, row 1 here represents observation 1. Column 2 represents observation 2. We see the Euclidean distance between the two is 2.56. If I want to simply access just that particular distance, I can say dist.mat, row 1, column 2, as you might expect. That's going to be important shortly. Okay. Now to do the plot, I'm going to put the plot I'm going to make the plot square because I'm going to control the x-axis limits and y-axis limits to be exactly the same size. The reason why I do this is so that the distances that we see on this plot are actually the true distances. Now I'm going to plot on the x-axis variable 1, y-axis variable 2, plotting character 16, that's going to give me my, my dots, color going to be blue, and the size of these dots is going to be 5 times the normal size. Okay, and so there are my observations. Now in order to plot the actual distances between the observations in that plot, and also to draw lines between the observations in the plot, I use what are called 2 for loops. Excuse me. And essentially what happens is this, if you've never seen a for loop before. The first time through the for loop, so I say for I in 1 to 3, and I start some stuff with inside these brackets. The first time through, I is going to be equal to 1. And then in the inner loop, I have for j in 1 to I plus 1 to 4. So the first time through this, j is going to be set equal to 2. Now, with I equal 1, j equal 2, I want to do the following. I'm going to draw a line segment between observation 1 and then observation 2. Notice the I and the j there. It's going to be a line type of solid. Line width is 1, color is 2. If you remember, that's a red color. Then also what I'm going to do is at the midpoint between these two observations, I'm going to plot the actual distance. So here's the midpoint with respect to the x-axis scale. Here's the midpoint with respect to the y-axis scale. The actual text I'm going to plot, I pull out from my dist.mat matrix, I pull out the actual distance between observation I and observation j. So in this particular case, I is 1, j is 2, so I'm going to pull out that same distance that I had shown you right there. Okay. Then this marks in the end of this inner for loop, and then what happens is we come up to the top. Now j is going to be reinitialized to be 3, and so now I'm going to do exactly the same thing for observations 1 and 3. Get to the end, come back up, I'm going to go to j equal 4, do the same thing for observations 1 and 4. And then once I hit the end here, notice j would be 5 next, but I've only said do for j equal 2 to 4. So because of that, we exit out of this particular inner for loop, and we come up to the original for loop. And for I in 1 to 3, we've just done 1, so now we initialize this at 2. Now we go back to the inner for loop again, so that means we start at j in I plus 1 to 4, meaning 3. Now I do this for observations 2 and 3. Hit the end, go to observations 2 and 4. I hit the end of this particular for loop, come back up, I becomes 3, j is 4, do it one more time. A great way to see what happens is that this little part here that I have commented over will actually print off the corresponding information about what is I, what is j, what is the distance at each part of the for loop. We took a look at the cap function, if you remember, in the introduction to R notes. It's just a nice way to be able to print information inside of R. So let me go ahead and run that. I'm going to remove some of these extra labels here. I'm going to run that, and we can see now all the lines are drawn, all the distances are put in there, and we can see how R is going through each step of those two for loops. Now the last part then of doing this plot is I use the text function in much the same way as we've done before to actually label the actual observation numbers on the plot. So there you go. That's how you can do the plot. Okay. So then that takes us to page 13. Okay. Now we saw the dist function is one way to actually calculate the distances between each pairwise set of points. Another way to do that is use the daisy function. It comes out of the package called cluster. The daisy function works simply like this. The x argument, you put in your data. The metric argument says, well, how are you going to measure distances? I'm just going to use simple Euclidean distance. There are other distances available inside the daisy function. Look at the corresponding help for that if you're interested. And then one nice little thing about this particular function that's not in the dist function is that you can say use the standardized distances. So if I would put true here, I would be calculating the standardized Euclidean distance. I left it at false because we're not using standardized Euclidean distances for this problem, and this is what we get for all those distances. Now, of course, with this daisy function, while it's nice to have that stand arguments, maybe not necessarily a big deal, because what you could do is simply use the scale function first, then use the dist function to find standardized Euclidean distances. Okay. Now, you might remember me telling you last time that that the reason why there's so many different clustering methods is because there's not necessarily one best method out there. And so when we talk about these particular clustering methods, I'm going to talk about advantages and disadvantages with them. So we were talking about the nearest neighbor method, and one problem, sometimes it's a problem, sometimes it's not, one problem that can occur with this method is that it can produce elongated clusters. And depending upon the situation, this may or may not be desirable. Here's a little plot that helps demonstrate what I mean by elongated clusters. So here at the top here, well, we've got two variables, x1 and x2. At the top there we have this nice little compact cluster. It's kind of circular in nature. We also have a nice cluster like that here. Then the cluster that's in between is this elongated cluster. And it makes sense for this particular problem, or where the data is arranged, for this elongated cluster to exist. But let's say instead, let me do some erasing. Suppose instead we have all these points up here moved up to there. So it's right next to that elongated cluster. Well, in that particular situation, we would not want to have that elongated cluster. Instead, we would like to have a cluster that encompasses all those particular observations. But with the nearest neighbor method, these elongated clusters are more likely to exist than with other methods. And this is a result of what's often referred to as chaining. Because if you remember, with this nearest neighbor method, we're only looking at the nearest observations to make a decision of should I join, let's say, two clusters together. And so by saying the word chaining, what you can have is something like this, where you have, let's say, some additional points, and they all end up joining together. In particular, where that might not be ideal is, let's say, if we have another cluster that forms right up next to that one up there. And that's an example of basically observations forming a chain. And we would prefer that not to happen for a cluster so close to another cluster that's fairly compact. In this particular situation here, it may be reasonable for that to happen. Okay. So we talked about nearest neighbor. Now let's talk about furthest neighbor. This is sometimes also called complete linkage. And what this means is essentially is that, and as you might expect from its name, is that instead of looking at the nearest neighbor between two observations to decide the distances between two clusters, we now look at the furthest neighbors, or the two observations that are the farthest from one another. So let me go back to this plot that we saw earlier for this four observation example. Let's go through the actual clustering process here. Now again, all observations start off in single clusters by themselves. And then to decide, well, which observations should we join to form the first cluster, we look at the smallest distances. And we can see that 3 and 4 has the smallest distance. Now to decide, well, what's now the distance between observation 1 and this cluster that has 3 and 4 in it, we look at the 2.44 there and the 4.02 there. The furthest neighbor method then says, let's go with the largest distance. So the distance between 1 and the cluster that has 3 and 4 in it is 4.02. Before, with nearest neighbor, we took the smallest distance and we had 2.44. Just to emphasize the point then, the distance between 2 and also the cluster that has 3 and 4 in it is given to be 3. Okay. So now then, well, which clusters are joined next? Well, we have the choice between the 2.56, the 3, and the 4.02. The smallest value then still corresponds to which clusters are joined. In this case, 1 and 2. Next, what's going to happen is that the entire, or these two clusters then are joined together to form one overall cluster. What's the distance between the two? Well, let's take a look. Again, we're looking at the largest, or the furthest neighbors, you could say. So we look at 2.83, we look at the 3, we look at the 4.02, we look at the 2.44. Based upon the furthest neighbor method, the distance between these two clusters is defined to be 4.02. Okay. So let's talk about some characteristics then of this clustering method. This method, as opposed to the nearest neighbor method, tends to form more compact clusters. And the reason is because now we're looking at the furthest neighbor between the two clusters. So in order to actually join two clusters together, the furthest neighbors need to be closer to one another, thus forming more compact clusters, as opposed to the elongated clusters that can happen with the nearest neighbor method. Also, the furthest neighbor method can somewhat be distorted with the presence of outliers, because again, an outlier is a point that's, let's say, maybe far from the rest, and by the definition of furthest neighbor, well, the furthest neighbor might look towards that outlier when deciding to join clusters. Please make sure, and this is sometimes a confusing thing for students who are first seeing cluster analysis, is that while we look at the furthest neighbors to decide the distances between the different clusters, it's still the closest two clusters that are joined. This furthest part here, or the nearest part that you saw with the nearest neighbor method, only corresponds to how we define distance between clusters. Okay, so that was method number 2 for the agglomerata methods that we're going to discuss. Let's look at method number 3. This is the centroid method. Now we're going to define, let's say, the similarity, or the distance between two clusters, as the distance between cluster means. So as you might expect then, this particular method is going to perform somewhat in between the nearest neighbor method and the furthest neighbor method, because now we're kind of, you could say, going halfway between the furthest and the neighbor since we're using kind of an average value. So let's go back to that plot that we saw once again. Do some erasing. Okay. So again, to start off the clustering process, we look at which clusters are the closest to one another. Every observation is in a single in its own cluster. So 3 and 4 will be joined. Now, with the centroid method, to define the distance between 1 and the cluster that has 3 and 4 in it, again, what we look for is, well, what's then the average value between 3 and 4? In this case, it's right about here. It would correspond to variable 1 equal to 5, and variable number 2 equal to, let's see, 2.5. Okay? Simply, all I did was I took an average of the corresponding x-axis values for observations 3 and 4, and the corresponding y-axis values for observations 2 and 3. So now the distance between observation 1 and the cluster that has 3 and 4 in it is the distance between where observation 1 is located and this mean point. The distance between 2 and the cluster that has 3 and 4 in it is defined in a very similar manner. So let's go back to where we were on page 16 now. Okay. So I give you some code here that shows how you can find then this mean value for observation 3 and 4. I use the column means function that we've seen before. Notice I'm only using row 3 and 4 of the data set. Then what I'm going to do is simply use the rbind function, which means combine 2 data frames by row. So I'm going to take observations 1 and 2 out of set 1 and combine it with then these means from observations 3 and 4. And that's going to be a new data frame called set 2. And I put this set 2 then into the dist function, so I can find all the distances. So here we have the group the cluster that corresponds to 3 and 4. And so we see the distance between 3 and 4 and observation 1 is 3.13. Distance between the cluster with observations 3 and 4 in it and the cluster with just observation 2 in it is 2.69. Distance between 1 and 2, just like before, is 2.56. This is the minimum distance, so observations 1 and 2 are joined. Then, similar to what we had with furthest neighbor, we join the 1-2 cluster with the 3-4 cluster. So then the fourth method to do this agglomerative clustering is what's called the average method. Sometimes it's also called the average linkage. Note that this, because of the name average, this can be confused with the centroid method, but they are different. Simply, to define then the distance between 2 clusters, or the similarity between 2 clusters, we simply find the average of all distances between each pair of observations across the clusters. So let's go back again to that plot and go through the process. Let me do some erasing here. Okay. So again, observation 3 and 4 are joined to begin with. To find the distance between 1 and the cluster that has 3 and 4 in it, we simply take the average of 4.02 and 2.44. To find then the distance between observation 2 and the cluster that has 3 and 4 in it, we take the average of 2.83 and 3, and then that's the distance. So let's go back again to page 18 where I have those calculations done. Okay. So we see here the distance between 1 and the cluster has 3 and 4 in it is 3.23. Distance between 2 and the cluster has 3 and 4 in it is 2.915. Still, the minimum distance then of all those three distances is the 2.56 that then would join observation 1 and 2 into a cluster. And then the final step, the cluster with 1 and 2, is again joined with 3 and 4. So this average method then can tend to put together clusters that have small variances and also produce clusters with the same variance overall. Again, this average method is somewhat in between the furthest neighbor and nearest neighbor in terms of performance. So lastly then, there's the Warts minimum variance method. And this works a little bit like the centroid method, where what we're interested in is taking finding essentially the mean value for every observation within a particular cluster. Let's call that cluster A. And then subtract off then the mean value for all observations that are in cluster B. Take the transpose, do the difference again, and then multiply by this weight out in front, which corresponds to essentially how big the clusters are. And so that's how you find the distances, and then you can proceed in a similar manner to what we've done with the 4 other methods to make decisions about which observations are joined together into clusters. In the end, this method can produce clusters with a similar number of observations because we have that weight out in front. Okay. So some overall comparisons between these methods. Everett's book on cluster analysis has this nice little table that I would like you to take a look at that describes these particular methods that we've examined. It uses a little bit different terminology than what we have, but I think you can, generally speaking, figure out what they, I should say, mean. Some other resources to find out more about how these clustering methods work in terms of when they work better or worse is actually in the SAS online help for its corresponding proc that does cluster analysis called Proc Cluster. In this particular help, they actually reference this Milligan paper in a Psychometrica journal that talks about the different clustering methods and how they compare. It's a nice paper. And then lastly, in Dallas Johnson's book, he says the following: nearest neighbor tends to maximize the connectedness or the chaining of a pair of observations, pairs of observations, and creates fewer clusters than furthest neighbor. Furthest neighbor will minimize the intra-cluster distances, which produces compact clusters. And as I've been alluding to, the other methods kind of fall between these two. But I think a very good thing to understand with cluster analysis is that you should try more than one method. And then use various graphical methods. Some we've discussed already with simple scatter plots. But we'll also talk about other graphical methods that are helpful when you have more than 2 or 3 variables. Use the graphical methods to help you justify or make sense of the cluster analysis results to see if they're ideal. And that's how you can choose whether or not to use maybe, let's say, average versus furthest neighbor, and so on. Okay, so let's talk about determining the number of clusters to actually use. This can actually be a difficult thing to do. Again, with these agglomerative methods, you start with having n clusters for the n observations, and they will continue until you get down to having 1 cluster overall. Now, having just 1 cluster kind of defeats the purpose of actually doing a cluster analysis then, because with the cluster analysis you want to find distinct groups of observations. And so the goal then is to figure out somewhere between n clusters and 1 cluster to go with. Ideally, you would like to have something that's a lower number in terms of closer to 1 than closer to n. And so the purpose of the next few pages here is to describe to you, what's a good cluster, what's potentially a bad cluster, maybe what you would like to avoid when you're doing your cluster analysis. And this will lead you then to determine when you should stop the clustering process so that you don't get all the way down to having only one cluster. So here's an example of a good and a bad cluster. So we have this, and we have two variables, x1 and x2. And so we have this nice, compact cluster of similar observations. But then over here on the right-hand side, we have this cluster that looks like it's actually maybe should be two different clusters, one here and one here. Now, I do label this as a bad cluster. Maybe it's better to say not ideal in most situations. There might be settings where, obviously the observations here are more close, are more similar than the observations over here. But in most situations, though, you would not like to have this cluster and this cluster actually join together. And so, how do you determine when this happens? Well, there's going to be ways that we can look at to examine the distances between two clusters when they're joined. And we can see here that when points are being joined together in a cluster, we can see that they have small distances, relatively small distances here as well. But once we see two clusters that are joined together that has a large distance, then that should be a warning to you to think that, well, maybe I should stop the clustering process before I get to this point. Maybe I shouldn't join these two clusters together. And that's the key aspect. It's easy to see when you only have two variables. But when you have, let's say, more than three variables, it's a lot more difficult to see this. And we'll look at some graphical techniques to help us see this. Here's another example of a good and a bad cluster. So, again, we have this nice compact cluster here of like observations. But over on the left-hand side here, we have this observation that you would think would go into the purple cluster, but instead goes into the yellow cluster. This could happen in situations such as with furthest neighbor, because we can see the furthest neighbor here is maybe at about the same distance as the furthest neighbor to that part right there. And so what typically will happen in application is that you'll get to a point that might look something like this, where you have actually four clusters, and and then the clustering algorithm needs to decide, well, where does this particular observation go? And notice when this decision's made about where this observation is going, if you're using furthest neighbor, you'll note that the distance between this point and here, is kind of large. Where previously the distances maybe had not been as large. So this, again, just like in the previous example, this is a warning to you that, my distances now have kind of increased in size when deciding to join clusters together. So maybe I should stop and not actually join this particular observation to the yellow cluster. And you might be just left with four clusters. Well, this also helps demonstrate a situation where maybe the clustering method that you've chosen is not adequate, because we can see from just looking at this plot, this particular point, generally speaking, deserves to be in the purple cluster, or should be in the purple cluster, because it's more similar to that than the yellow, or just being by itself. And so when we see something like this, we might decide, okay, let's try a different clustering method where, in fact, that point is joined to the purple cluster. So next, let's talk about graphical tools that we can use to determine if a clustering method has come up with a good set of clusters, or also determine, well, when we should stop the clustering process. Obviously, if you have 2 or 3 variables, scatter plots of the data can be very helpful. If you have more than 3 variables, well, principal component analysis could be used so that you can actually plot the data in 2 or 3 dimensions. Also, a parallel coordinates plot can be very helpful to see which observations are similar and which are not. But a tool that's a new tool that we can use is what's called a hierarchical tree diagram. And what this tree diagram does, it essentially tells you or shows you what the distances are between clusters as the clustering process continues to a point where it gets to one cluster. To help explain that, let's take a look at this simple hierarchical tree diagram for that 4-observation example. So we see here at the top, we have the different observations represented by their numbers, and then represented vertically, we have their distances in terms of the distances between the clusters. And so if you remember with the nearest neighbor method, actually all the methods, the observations 3 and 4 were joined first, and the distance between 3 and 4 was 2.24. So in this hierarchical tree diagram, we have what are called branches that are drawn at a length of 2.24, given what the vertical axis is, and then we connect then these branches together to signify that these observations are joined together in a cluster. Then next, with the nearest neighbor method, at a distance of 2.44, observation 1 was joined to to the cluster that had 3 and 4 in it. So again, we draw a branch that goes all the way down at a distance of 2.44 relative to the vertical axis, and then we connect then that to the cluster that has 3 and 4 in it. And then lastly, a similar thing is done with observation 2 when it was joined with the cluster that has 1, 3, and 4 in it, so that overall you have one cluster. So some other things to understand about this plot is that the plot doesn't have to be drawn exactly like this. Instead, what R actually does, it puts then the observation numbers down on the bottom, and then forms the branches going up. You'll see other software packages draw the tree in a horizontal manner, so the branches are horizontal versus the vertical that you see here. Also, another thing to understand about this plot is that if I were to draw, let's say, a vertical line across, horizontal line across there, notice it intersects the branches 4 times, meaning that I have 4 clusters at that particular, if I were to go to this particular distance. If I were to draw a horizontal line here, notice it intersects the branches at 3 spots, meaning that I have 3 clusters at that point. If I were to draw a horizontal line there, notice it intersects the branches at two places. That means I have 2 clusters at that point. And then eventually, once they are all the observations are joined together, if I were to draw down another branch like this, I would have 1 cluster. That's going to be a very important point coming up when we use these tree diagrams to help us decide when to stop the clustering process. Well, how is that done? Well, remember before, when we were looking at the good and the bad clusters, a way to determine when I am maybe, let's say, overjoining the clusters is when I start seeing large distances. So when you start seeing large distances between clusters that are being formed relative to all the other distances in the plot, then that tells you, maybe I shouldn't be joining some clusters together, and I should do what's called cut the tree. So you can cut the tree at a particular location, at a particular distance, and then figure out, well, how many clusters that corresponds to, and also the cluster memberships. I think that will be more clear when we get into now this new example. So towards the beginning of these notes, we looked at this 2-variable data set that had 14 observations in it. Now to help, this is a plot of the data. Now to help make this more real, what I've decided to do is actually standardize the data. that's typically done in cluster analysis, if you remember the discussion about that. And so I have Z1 plotted on the x-axis, Z2 plotted on the y-axis, and here's my standardized data. And what we saw with these 14 observations is perhaps 5 clusters in terms of 5 sets of observations that are similar to one another. Or alternatively, maybe instead, let me get my purple pen out, I have one cluster here, and I have one cluster here. So what we're going to do next is look at one of these hierarchical tree diagrams that help us diagnose, or help us determine, I should say, how many clusters are appropriate for this data set. So let's go back up to page 26 then. Okay, so the main function that we're going to use in R to do this, to do agglomerative clustering. Remember, agglomerative is a special case of hierarchical. Is the H-clust function, H for hierarchical. And so we're going to use the H-clust function with standardized distances between the data points, or I'm sorry, standardized data. And actually we're going to pass into it the standardized distances. And then we're going to get some results out, put into an object. And with this object, we can use then the plot function to plot a hierarchical tree diagram. So again, the steps. I'm going to standardize the data first using the scale function. Then I'm going to find all distances between the standardized data, and with that, pass those distances into the H-clust function, and then specify I want to use the nearest neighbor method. Okay, so here's the code. Let me actually jump on over here to my program. So I'm going to put my vector, put my data into an object called set1. So there's my data. Going to standardize it, and here's then just the plot that we had seen previously using the same techniques that we've used in the past. Then I'm going to then use the dist function to help me find the Euclidean distances, or I should say the standardized Euclidean distances. Put then an object called dist.mat, just to show it to you here. You can see that for 14 observations, I have all these distances here. Then using H-clust, for the D argument, I'm going to use the distance matrix. And then for my method, I'm going to say single. If you remember from last time, single linkage is another name for the nearest neighbor method. I'm going to put the results into an object called clust.nn for nearest neighbor. And let's print off that object. So when I print off the object here, you can see that what's given to you is not very useful. So instead, what we can do is type names clust.nn to see what information is actually inside there. And what we have here is a lot of information that can be used for to draw the hierarchical tree diagram. In particular, if I do clust.nn $merge, what's represented here is the history of the clusters being formed. Okay, so the first cluster that's formed is joining observation 13 with 14. If we take a look at the plot over here, if you see where my mouse is, that makes sense for that to be the first cluster to be joined, or first cluster to be formed. Now the reason why I know that these are observation numbers is because I have a negative sign out there. This is just the syntax that the function uses. Now the second cluster that's formed is for observation 1 and 2. And we can see, again, where my mouse is, you can see that those points are fairly close together too. And so it makes sense for them to be joined together. Now the third cluster that's formed in this hierarchical process is observation 3 is then joined with, notice there's just a 2 there, it's not a minus. What that means then is that this 2 represents cluster number 2. So that second cluster that was formed. So in other words, 3 here is joined with 1 and 2. Next, observations 10 and 12 are joined together. So you can see that in the plot. Then observation 11 is joined with cluster number 1. What's in cluster number 1? Observations 13 and 14. And again, if you look at the plot, that makes sense. Okay. Let me come back over here. Now we have some other information that's also available to us, such as the height argument. This corresponds to then when these clusters were joined together, what was then the standardized Euclidean distance. So for the first cluster then, between observations 13 and 14, the standardized Euclidean distance is 0.134. And you can see, because since this data set I just kind of made it up myself just to help illustrate the method, you can see that we have some duplicate distances. So for example, the distance between 1 and 2 also happens to be 0.134. But you see that also that we start getting to a point where some of these distances are much larger in comparison to, let's say, some of the previous distances. In particular here, the last distance is 1.72. We'll see what that represents shortly. Okay, so let's see here. I just want to make sure I am talking about everything I want to talk about. Okay, so to do the hierarchical tree diagram then, we take the results from H-clust. We put this into plot. Now remember, plot is a generic function. And so what R does, it first looks at, well, what is the class of clust.nn? And so that's what I did here, H-clust. And then it looks to see, is there a method function called plot.hclust? And what do you know? There is. And so this then is the hierarchical tree diagram. R refers to as a cluster dendrogram. Both terms are widely used in cluster analysis. Okay, so now what we see here is that the observation numbers are represented at the bottom. And we see branches going up versus going down in my original description. This height here then corresponds to the distance, how the nearest neighbor method finds the distances. So, for example, remember observations 13 and 14 were joined first. The distance that we had there was 0.1346. Let me actually get a thinner pen here. Also, remember, observations 1 and 2 were then joined next, and they happen to be at exactly the same distance. So that's why you see these branches going up to the same height. Next, based upon the height component of clust.nn, we see the next distance that has observations joined together was at 0.202. And so here's 0.202. And if you remember, what actually occurred next was that observation 3 was joined with the cluster that had observations 1 and 2 in it. And we can see this happening here with these branches going up and being joined. Okay. Now next, what we like to be able to do is take a look at this tree diagram and look at where we start seeing large distances between clusters that are joined together, and cut the tree at those distances. Now immediately, what should be obvious to you is that when the method ends up joining, let me do some erasing first. When the clustering method ends up joining this 11 through the 12 with the 7 through the 5, we see that we have these long branches, and they're drawn out to this. I'm getting this from the height component of clus.nn. They're drawn out to 1.72, and we can see that this is a big distance in comparison to the other distances that are shown on the plot. So because of that, I'm going to draw a horizontal line across the plot and cut the tree there, where I have now two distinct clusters. So I definitely know I don't want to go up to one cluster, which is what will be represented here, because we have such a large distance that's needed to get up to that one cluster. And so if I were to stop at two clusters, then I would have these two clusters here. And what do those two clusters correspond to? Oops. Simply what you see already drawn on the screen here with the purple clusters. If you look at those observation numbers compared to where I cut the tree. Okay. Now, well, are there other places that I could cut the tree? Yeah. Again, we're looking for large distances relative to maybe what was happened before. I'll leave that there. And what I see here, for example, is maybe right here. Notice how the distances are much larger than what they were previously in this process. And notice that this corresponds to 4 clusters. One here, one here, one here, and one here. Okay, well, what does that then correspond to in our plot? Well, it's not the 5 clusters. Instead, what it is, get my eraser out. Let's see. It's in the upper right-hand corner, those observations join together, and then we have 3 other clusters represented down there. And so what that represents then for us is that 2 clusters is reasonable, 4 clusters is reasonable too, based upon using the nearest neighbor method. Now you might be thinking, well, what about 5 clusters? Well, notice here that is a possibility, but notice what happens when I draw this across. I actually end up maybe getting 6, depending upon where you draw it. And then the distance between joining here, between 4 and 5, and joining here, this large group is not that big. So because of that, it's hard to justify having 5 clusters using this particular method. 6 perhaps, but 5 is hard for this particular clustering method. This will not necessarily always be the case for the other clustering methods, though. Okay, instead of simply drawing lines on the plot corresponding to where I cut the tree in terms of drawing it with my tablet PC pen, let's look at how we can have R draw the lines across the plot where we would cut the tree. So let me come back over here to my tin here, and let me find this here. So again, I'm going to do a plot, the hierarchical tree diagram using the plot function. So there's my tree diagram. And then what I need to do is figure out, well, where do I want to draw the line? Well, I can use the AB line function to draw horizontal lines on the plot. So I say a horizontal line at 1. How about we make it a dashed line to differentiate it with the solid lines that you already see on the plot? And just so that we can see a little bit better, how about a line with a 2? So when I do that, then we can see how that tree is cut at height, or a horizontal line at 1, or height of 1. And also I'm going to draw a line at 0.4 as well, and that shows us the 4 clusters that we had identified previously too. Okay. Well, how can we then have R automatically tell us then, well, which observations are in which cluster for at a particular cut point here? And that's where then the cut tree function comes in handy. Notice it's not actually cut tree, it's actually cut tree. I guess they just didn't want to put 2 T's together. So we say cut tree. I'll pronounce this cut tree. And then for the first argument, tree, you put in the results from each cluster. And then at what height do you want the cut to be made? So if I do a cut of 1, if you remember that corresponded to 2 clusters, then I put the results into cluster 2. And how about we just simply print off the results? And so we can see then the observations corresponding to their cluster number. So to help see this better, if I construct a data frame here with set 1 and also cluster 2, we can see that observations 1 through 8 are in cluster 1. Observations 9 through 14 are in cluster number 2. Now alternatively, you could also specify, well, how many clusters do you want? Let's say, if you remember when I drew the line at point 4, that corresponded to 4 clusters. How about if I use k equal 4 as an argument, and this tells then R how many clusters I want. So I'm going to put the results then from that using cluster 4. And you can see there is my new set of clusters. So if I combine this again with the data frame that we had before, you can see, for example, observations 1 and 3 are in a cluster, observation 4 and 5 are in a cluster, and so on. Now, by doing this, then it allows you to identify which observations are in what cluster. Also, this allows you now to construct plots that help you visualize, do these clusters make sense or not. So one way to do a plot then is to use the plot function. I'm going to pull out the first column in my standardized data. Notice I'm using standardized data versus the actual observations. I purposely do this for the plot because the cluster analysis procedure actually operates on standardized data. Y-axis, we'll put variable 2 or column 2. And the main thing to pay attention to here is the plotting character. I'm going to use the numbers that are in cluster 4. So for example, plotting character of 1 is going to be an open circle. Plotting character of 2 is going to be a triangle. Then also with respect to the color of the plotting point, I'm going to specify the cluster 4 too. So a number 1 is black, number 2 is red, and so on. The way that I know that is that R has set up a function called palette that identifies 8 colors with respect to numbers. So you can go up to 8 clusters using this idea. And so then if I simply do my plot as well, you can see that I have the 4 clusters, the 4 observations there, identified uniquely by the different plotting characters. Now, R also has other methods that are available to us to help determine cluster membership. Again, meaning which observations are in which cluster. And so if we look at page 32 here, we see that there's a function called RECT for rectangle.hclus. And what this does, it allows you to draw rectangles on your plot corresponding to the clusters. So to use this function, simply the first argument, cluster.nn, number of clusters that you want, 4, and what color do you want the rectangles to be drawn in? Let's say red. I'm going to save the results into something called save.cl, and we see we have 4 clusters that are identified here with the corresponding observation numbers in each cluster. And on your plot then, these red diagrams then are drawn corresponding to the cluster membership. So that can be a little bit helpful to determine which observations are in which cluster. Now, so far we've only looked at the nearest neighbor method applied to the this 2-variable data set. Let's take a look at some of the other agglomerative methods. So let's look at furthest neighbor. Now remember, another name for furthest neighbor is complete linkage. So I'm going to use the h-clus function here with a distance matrix of the standardized Euclidean distances, and then I say method equal complete. It's just a terminology that R uses. Put the results into clus.fin, and then I merge then the order of the clustering with the corresponding heights or distances as specified by the furthest neighbor method. So similar to what we've found before with nearest neighbor, observation 13 and 14 are joined. Then observations 1 and 2 are joined. And then notice that observations 10 and 12 and observations 6 and 8 are joined. This differs a little bit from what we had with the nearest neighbor. Then I could do I'll use a plot function with clus.fn to get the hierarchical tree diagram. After I view the actual plot, that's when I tell R to draw particular lines for where I want to cut the tree. And here's the actual hierarchical tree diagram. Now obviously on this plot we see that going up to one cluster is not good because there's a very large distance here, so that's why I cut the tree at about 2. Also we see some long distances between then the successive clusters being formed here, so that's why I decided to draw a line at about 1.2 or 1.25. And notice how that corresponds to 3 clusters. The line above it corresponds to 2. There might be a little bit of justification here too for also having 5 clusters as well, because you see somewhat of a larger distance relative to the distances that we had been seeing before. But I think 2 or 3 are definitely the most justifiable. Well, let's look back at what those particular clusters represent. So if let's just look at 3 here. Well, notice it corresponds to the points that were in the upper right-hand corner as one cluster. Then 6, 7, and 8 is one cluster, and 1 through 5 is the other cluster. So let me go back to my plot. Now let's actually keep on going to where the numbers are. There we go. So this set of clusters by furthest neighbor then ends up with these as our corresponding clusters. And that does make some sense. I mean, we do see that a little bit larger distance here between the points. Let me go back now. Okay. Now let's do next Warts method. So same kind of code as before, except for I'm going to put a ward there instead. And we can see the ordering of what the clustering was done. And here's the corresponding plot. I cut trees at 2 clusters, and so I drew a line there, and also at 3 clusters, and I drew a line there. I don't think any other number of clusters would be justified by taking a look at this plot. And notice that these corresponding 3 clusters are the same as with furthest neighbor. In fact, all the agglomerative methods agree that 3 clusters may be sufficient, except for the nearest neighbor method. Okay. So now there are, as I said, there's many other functions out there that can be used for cluster analysis in R. In particular, for these agglomerative methods, another popular function is one called Agnes from the cluster package. This function was originally, or this package contains a set of functions that were originally written in S+. If you remember from our introduction to R class, where we talked about the history of R, S+ was a commercially derived software package from the original S language developed by AT&T Bell Labs. S+ came about in the 1980s. In fact, when I was in grad school in the 90s, since R didn't exist, I used S+ at times. And anyway, so this package corresponded to a book by Kaufman and Rousseau on cluster analysis. I have code in my corresponding program that shows how to use this function. In particular, some nice things are about it is that a data frame rather than a distance matrix can be given directly in Agnes, which I think is a nice thing to do rather than us having to do an additional step. But you got to be careful with respect to what the stand argument in Agnes means. You might think that corresponds to standardize the observations just like what we had done previously with scale. In fact, it doesn't quite do that. Instead, what it does is it mean adjusts the data, so it takes each observation, subtract off the variable's mean, but then divides by the mean absolute deviation instead. It's just a different way to go about trying to put the data on the same kind of scale. In addition to a hierarchical tree diagram, this package also allows you to do what's called a banner plot, which basically gives you the same kind of information that the hierarchical tree diagram does, so that's why I'm not going to talk about it here. Okay. Now, there are other methods available to determine the number of clusters other than the ones that we've seen so far. Dallas Johnson's book and other SAS-based sources have advocated numerical measures based upon classical multivariate methods. So, for example, what we'll see later in the semester, there's an extension of a two-sample t-test where you want to test if one mean is equal to another. The extension to a multivariate setting would be to test whether or not one mean vector is equal to another mean vector. And so, using that that kind of measure, it's actually called Hotelling's t-square. One can, without going into all the details, help determine when the clustering process should be stopped or when it should keep on going. Now, outside of SAS-based sources, I have not seen these methods discussed or even recommended, or even discussed. I should put it that way. When I've taught this course in the past, when I had used SAS, I had actually discussed these topics. I chose to not to this time. Then I'm using R, since there are not easy ways to implement these methods in R. And also, I don't really see anybody else recommending them other than SAS-based sources. And in fact, corresponding to our recommended books for the course, the two R-based ones, they don't even mention these methods. So you're not responsible for any of these other methods to determine the number of clusters. I just wanted to point out that other methods do exist.